So let us begin the last lecture in this series of discussions on gravitation. So what we are going to do today is to wind up the discussion on gravitational potential energy and then the escape velocity, following which I am going to discuss a little bit about satellites, and finally the implications of Newtonian gravity to cosmology, because after all we call it as universal law. Therefore, it is a good question to ask what it tells us about the large scale structure of the universe. There is yet another topic which is quite important, although we may not realize it at this particular point, and that is the concept of weightlessness. So this goes back to the equivalence principle that I discussed at the very beginning of this set of lectures. So we will also discuss that. What we did was to start looking at escape velocity. Essentially almost everything that we discuss will be using gravitational potential energy concept. So what I did was to imagine that I have the surface of the earth, this is my radius r, and there is a body here which has to be short, let us say perpendicular to the surface at that particular point, so that it escapes away to infinity. Escapes away to infinity. Which means to say that as time becomes larger and larger, it goes farther and farther away. It will not be bounded by any distance. If it gets bounded by some distance, of course, either it will return if it is shot perpendicularly upwards, or if it has a horizontal velocity, it may either return or it may get into an elliptic orbit. And that is what we mean by satellites, when it gets into an orbit. But right now, we are interested in the escape velocity. So escape velocity is the minimum velocity which is required to free this body, whatever, let me call it as A, from the gravitational field of the earth. So what we did was to look at the kinetic energy and potential energy at the surface. So we wrote half m v escape squared minus g m by re, where re is the radius of the earth. This is the total energy of the body, and that should be conserved as the body moves along the field of the earth's gravitational field. But now I am asking for the minimum energy, and therefore the minimum kinetic energy, and therefore the minimum velocity, which I call the escape velocity, and that would happen if the particle were at rest far, far away from the earth. Therefore, we put this equal to 0. So once you do this, as observed, my masses are going to cancel, and we get a neat expression. Escape velocity is simply given by root 2g mass of the earth. So let me write E clearly, divided by r of E. So as we said, the escape velocity is independent of the mass of the body which is trying to go away, a rocket, let us say. We may not like to remember all possible values. For example, you have the gravitational constant, you have the mass of the earth, you have the radius of the earth. So what we can do is to rewrite it in terms of another constant, min, which you are all completely familiar with, and that is the acceleration due to gravity at the surface of the earth. So I am basically revising whatever we did in the last lecture. So we are going to write mg equal to g me m by re squared. In writing this, we are of course assuming that the earth is a perfect sphere and it is not too bad an approximation. Again I cancel. So gme by re is nothing but gre. Therefore I can write my escape velocity to be 2g into radius of the earth. And we all know g is of the order of 10 meters per second squared. That is what it is. G equal to 10 meters per second squared, and radius of the earth is roughly 6400 kilometer. So if you substitute, you will get a velocity around 11.2, 11.3, 11.6, etc., etc. So whatever it is, so let us say it is of the order of 11.5 kilometers per second. And we got an idea of how large or how small this velocity is by comparing it with some of the known velocities of the very fast flying jet planes and cars, so on and so forth. In fact, it is large enough to require us to develop very special technologies, rocket technologies, in order to escape. For example, when the Apollos were launched by the United States, by NASA, they had to really work hard because the rocket had to escape from the gravitational field of the earth and go as far as the moon is. So this is what we have. Of course, if we were to try to escape from the surface of the moon, then moon is much lighter than the earth. Therefore, the escape velocity will become smaller, probably about a few kilometers per second. I am not very sure of that. And it is generally argued that it is for this reason that the moon does not have any atmosphere. Of course, we should be very careful about making such a statement because that assumes that 2.5 kilometers or whatever that magnitude is available to the gas molecules. That would depend on the temperature of the gas, RMS velocity of the gas. So presumably what you should do is to go back, look up your books, look up the internet and check what the temperature of the moon is, because on the one side it is very cold and dark, on the other side it is always bright. It is always one side of the moon that faces the sun. The other side is perennially dark because its period of rotation is roughly the same as the period of revolution. That is the reason. So probably the temperature is large enough for the gas molecules to escape. So please work that out and convince yourself to check whether such a reasoning is correct or not. So nothing should be taken at its face value. Now this 11.5 kilometer per second, the number that I obtained, assumes that the earth is stationary. It is at rest. But what is reality? Reality is that the earth rotates about its axis. At this point, we will ignore the fact that the axis is tilted at 23.5 degrees. That of course is extraordinarily important because it is this tilt that is responsible for seasons, etc., etc. Let us ignore that particular fact. Now the earth is rotating about its axis, therefore earth is not an inertial frame. Earth is not an inertial frame because if there is an observer who looks at us, since we are bound to the earth, we are moving together with the earth with the same angular velocity. So let me indicate that my earth is rotating. So these are my latitudes, these are my longitudes. So let me look at this point on the equator, which is very convenient. My earth is rotating about this particular axis, let us say. Then we know that V equal to omega r. That is what we have. In fact, I should write it as Re. There is a certain velocity. And my acceleration is given by omega squared Re. So there is a certain force that is acting on us because of which we are rotating together with the earth. We are a part of the earth and there is a continuous spin that is taking place. But from the viewpoint of the earth's surface itself, we are not accelerating. And remember, this acceleration is inwards. This is inwards acceleration, because anything that has a circular motion experiences a centripetal force which is inwards. So from the viewpoint of an observer in the free space, in the outer space, the earth is rotating. So we are like a mass tied to a string from the center of the earth. So we are going round and round and round. There is a centripetal force acting on us. And that acceleration is given by A equal to omega squared Re. Again, you can write an m and you can cancel that. And that is one feature which is common between the centripetal force and also the gravitational force. It is given by omega squared Re, whatever it is. However, from the viewpoint of the earth, we are not accelerating, we are at rest. But in every frame of reference, if we want to balance all the forces, that means we have to include a fictitious force which is balancing this physical force. This is a physical force coming from the spin of the earth. There must be a fictitious force. So what we are saying is that in the earth frame, this is a very, very important concept. In the earth frame, we are at rest, and therefore there is a fictitious. What does fictitious mean? Unreal. It is not a real force. It does not have any physical origin like gravitation or electrostatic force or a spring mass system. Unreal force which cancels the physical force, the physical centripetal force. Which cancels the centripetal force. That is what it is. So this physical force is acting on it, and this is what is called as a centrifugal force. This centrifugal force is acting outwards, and therefore what we have is, if I look at the surface of the earth, then what is happening? There is a gravitational force which is acting inwards. There is a centrifugal force which is acting outwards, which is given by m omega squared Re. Where omega is simply the angular frequency of the rotation of the earth. That is what we have. Therefore, I would like to leave it as an exercise for you people to find out what is G effective. So let me write that for you. So what we have is, you have the earth here. So the gravitational force is acting inwards. The centrifugal force is acting outwards. So my G effective is nothing but G minus the acceleration coming from the centrifugal force, which I will write it as omega squared Re. That is what I should write. So please remember, omega equal to 2 pi by t, and the period is simply given by 24 hours, which is 24 into 3600 seconds. That is what we have. Now if you plug it in and find out the escape velocity, so please take it as an exercise. If you plug it in and look at the escape velocity, this will decrease. So I am not going to work it out as I told you, but the answer is that it will decrease by about a kilometers per second. I think 11.2 or 11.3 will become 10.4 or 10.5. It's about a kilometer per second. That is what we have to remember. Now this requires a little bit more analysis. So if I am sitting on the surface of the earth, here the centrifugal force is everywhere acting in this direction. In fact, and the magnitude of the centrifugal force keeps on decreasing, and in fact here the force is 0 because omega is equal to constant but v equal to 0, because the velocity is equal to 0, force equal to 0. That means as you move from equator and you go towards the pole, your escape velocity, assuming that everything is thrown upwards, becomes smaller and smaller. So this is another exercise that you people can work out, and what you find is that there is a not too insignificant but not too large variation from the equator to the north pole. So please work it out. So the problem is difference between the escape velocities at the equator and the poles. By the same token, the escape velocity will also depend on how you throw the object. For example, I can throw it in this direction or in this direction. So this is another thing that you can look at. So again, you can add your forces vectorially and you can find out what happens. So one is the equator and the poles, and another is direction of, let us call it ejection. Direction of ejection. So please work out both these problems and then you will get a fair understanding of the concept of escape velocity. The computation of this was extraordinarily important because, as I told you, this is what led to the development of the great technology starting from 1950s or even earlier that was made use of in order to develop the rockets that would escape from the surface of the earth. There was one Indian who was quite an expert in rocket technology, not to send it out of the earth but as a military tool, and that was the great Tipu Sultan. So that is something that is celebrated by the rocket community, that he had developed very, very efficient rockets because he had worked out the trajectory so well that it would go and hit the enemy installations. So this is about the escape velocity. What I want to now do is to look at the concept of potential energy and equilibrium in a slightly greater detail, and this has some very interesting and important lessons for us, which tells us that we should be very, very careful in drawing conclusions without looking at things carefully. So let me start with two masses, let us say, of capital M, and let me look at a small mass m right at the midpoint. We would like to contrast this with two equal charges QQ. Now I have to be careful. In the case of masses, I don't have to worry because gravitation is always attractive. Electrostatic is both repulsive and attractive. And what I will do, I will put a small charge which is also of the same sign. Here, all the charges are of the same sign. Basically, what we are saying is that the larger charges, the plus Q's, capital Q's and capital M's are fixed. They are not free to move. Take them to be very, very heavy. Here, take the charges to be very, very heavy. But whatever is in the middle is free to move. And let us look at a rectilinear motion. Let us say that this charge is tied to a bead, this mass is tied to a bead, and then these small masses are there. Now what is happening in the second case is that both the charges at the end are repelling the central charge. So what happens? If I move a smaller charge to a certain extent in this direction, then what happens? The repulsion here becomes smaller, but the repulsion here becomes larger. Therefore, the particle tends to move to the right. And if the charge moves to the left, then the repulsion here becomes larger, therefore it starts moving to the right. So whatever your displacement is, the restoring force is in the opposite direction. In fact, it is a very simple example which all of you people work out many times. It executes a simple harmonic motion. So if the perturbations are small, it is going to execute a simple harmonic motion. That means we say that this point, the middle point where the total force is equal to 0, where the force is equal to 0 is a stable equilibrium position. Stable equilibrium position as far as one-dimensional motion is concerned. Now of course, I cannot dictate that this small q should move only along the line connecting plus q, the two charges. For example, it can move in this direction, or let us say in this direction. A simple analysis will tell you that if it did that, the particle will escape away. In other words, this stability is guaranteed only if it is constrained to move along the line connecting the two charges. Even the slightest displacement, either above or below this particular line, will make the charge move away. All that you have to do is to make use of your law of addition of forces. Add them vectorially, you will see that it is not going to work out. So one says that electrostatics does not give you a stable equilibrium. Now what you can do is you can try to find out, of course this is not a general result. The general result that any configuration of charges will not give rise to stable equilibrium is something that you will study probably in your 12th standard, or if not when you go for higher studies. But the point in the case of gravitation is even more dramatic, because even along a line there is no stable equilibrium, because what happens? At this point the total force is equal to 0. The minute I move my mass slightly in this direction, the attractive force from this becomes weaker, the attractive force from this becomes stronger, so it will simply continue to move in this direction, it will never come back. So you give the most gentle push, the most gentle nudge, the particle will go away in this direction. And again you can play around, for example, by putting two masses here, so on and so forth. You will find that in any such configuration, it is not possible to have a stable equilibrium position. There are always points of total zero force, but then a slight disturbance from the total zero force is going to disturb the equilibrium, and that is a consequence of gravitational law. That is something that we have to remember. Now when Newton formulated his great laws, the first law, the second law and the third law, he had the idea of absolute space with respect to which everything moves. And the big question that was raised was, what is the frame of reference that gives me absolute space? Because after all there are so many frames of reference. So if there is water flowing and then there is a boat, water is flowing with respect to the bank, the boat is flowing with respect to water, let us say it is all at uniform velocities, so on and so forth. In fact, this is not an example just given out of the blue, because for example, Aryabhatta says that just as for a person in a boat in a stream, all objects at the banks appear to move, in a similar manner, because the earth is rotating about its axis, for a person on the earth, the stars appear to go around the sun. It is one of the most famous statements that he made. So there is always relative motion. And even if you look at our own earth, the earth is rotating about its axis, or the earth is going around the sun, and the solar system is traversing around the Milky Way, so on and so forth. Therefore, if I say that there is an inertial frame of reference in which Newton's laws are valid, then I need a physical approximation, if not a physical example, a completely accurate example of an inertial frame, because if it were not there, this formulation would be useless. So what did Newton do? Newton looked up the sky and looked at the fixed stars. We know that far away the stars do not have any relative motion among themselves. and they all appear to be at rest with each other. And it is because of this that we are able to have the ideas of constellation. The shape remains fixed. So we say Aries, Taurus, Capricorn, Sagittarius, or in our own language we say Mesh, Rishabh, Kumbha, Meena, whatever. Okay, these patterns are fixed. So Newton postulated that God has given the example of an absolute space, the with a capital D, T, okay, inertial frame, which is fixed in the fixed frame of the stars, because the stars are all fixed. Now the question is, why is it that the stars are not moving even if they are all gravitationally attracting each other? And the answer to that was that Newton said that the stars are all uniformly distributed in space. So if you imagine an infinite space and there is a uniform distribution of stars, so you take any point on the sky, then there is a uniform distribution of stars all around, up, above, below, whatever. Therefore, the net force on the star is equal to 0. So he argued that, look here, net force on the stars is 0. So every star is at rest. That is what Newton argued. So this is what is called as the static model of the universe. And it is with respect to these fixed stars, maybe our galaxy moves, our star moves, our sun moves, and we move. So this was in sense a sophisticated version of the Aristotelian idea where the earth is fixed and everything is moving around the earth. But you see, Newton's laws themselves tell us that such a model is untenable, because if there were a slight perturbation, then this equilibrium would be destroyed. Let us say one star moved away a little bit, then the neighboring stars would be perturbed, and this perturbation would grow, and it would be very, very difficult to sustain this idea of a static, homogeneous, isotropic universe. Homogeneous means it is the same if you move along any given direction. Isotropic means it is the same in every particular direction. So that is the model that we gave, and that is really a problem with Newtonian idea, although at the first instance it appears to be extraordinarily convincing. There is a more sophisticated version of that due to Stephen Hawking, but that you will study when you pass your 12th standard and go for higher studies, and when you read something called the Gauss's law, which you will do in your 12th standard actually. So making use of Gauss's law, one can show that such a universe cannot be stable. And indeed, as Hubble discovered, the universe may be homogeneous and isotropic, but all the stars are receding. In fact, the galaxies are all receding from each other following a law called the Hubble law. That is something that we have to remember. So stability is not guaranteed in the static case. Such a stability is not challenged when there is dynamics. For example, our planetary orbit, the Earth is probably a few billion years old. A billion is 10 to the power of 9 years, and it has been in a stable orbit. And presumably it will continue to remain in a stable orbit for many more billions of years. Eventually the stability will be lost. So we have to make a distinction between the static description of gravitation and the gravitational effect when things are in motion. That is something that we have to understand. So this is something which is useful for us to remember. What I will now do is to wind up the discussion on gravitation by looking at the concept of satellites. But there is one more piece of information that I should probably give you. It suddenly occurred to me, and that is about the second law. Second law of Kepler is of course a statement of conservation of angular momentum, but there is a certain qualitative understanding that you can have by looking at gravitational potential energy. So which second law? Kepler, not Newton's second law. Kepler's second law. Now let us say that you have the sun and the planet is in a circular orbit. Now what is happening? Along the orbit, T is equal to constant. What is T? Kinetic energy. V equal to constant. My gravitational potential energy. Why? Because R is fixed. Because R is fixed, V is constant. Because T plus V is a constant, my T is a constant, and that is what you solved. mv squared by R, and V is a constant. That is what you write at any given distance. But I told you that the Keplerian orbits are not necessarily circular, but it can also be elliptical. So what I will do is to now look at a highly elliptical orbit which is exaggerated. Okay, the sun is sitting somewhere here, it is one of the foci. That is something that you will study in your 12th standard in your conical geometry. The point of the nearest approach is called perigee, and the point of the farthest approach is called apogee. All these concepts are well known even in ancient astronomy. With respect to the Earth, this is called perihelion. Now with respect to the Sun, it is called perihelion. Helios is Sun, and this is called aphelion. Some of you may have heard of Einstein's general theory of relativity. There he speaks of the shift of perihelion of Mercury, just in case you have heard. Now let us see what happens. So this is maximum distance, I will call Rm or dm, and this is the minimum distance from the Sun, d minimum, d maximum. That is what I call. Now along the orbit, my total energy should be conserved. So what is happening? At this particular point, you look at the gravitational potential energy. At this particular point, you look at the gravitational energy. Again, I will leave it as an exercise for you people to figure out where the body should be moving faster and where the body should be moving slower. I will leave it as an exercise, and in some sense you can relate it to the Keplerian law, which says equal areas are swept during equal intervals of time. So this is one more thing that we can worry about. Now as the last topic, let us look at satellite motion. So when we speak of satellites, there are two kinds of satellites that we have to keep in mind, and this word satellite is peculiar to our solar system, because in principle all planets can be looked upon as satellites for the Sun. We are not worried about that particular part. So we are looking at the moons and the planets, moons of the planets. So planets have many moons. As I told you, the Earth has only one moon, Jupiter has probably 12 or such moons, Uranus also has many more moons. So these are called natural satellites. All moons are natural satellites, and they are of great interest to us because they tell us a lot about the origin of the solar system. If you study their behavior, how they were formed, so on and so forth. Then we have what we call artificial satellites. Which we are able to launch and which we are able to put around the Earth. So these are launched by us, the humans, so what it requires is rocket engineering, about which I will make a few more statements in a short while. Now there is no reason to spend a lot of time trying to convince you that these satellites play an important role. They play a great role in communication, in remote sensing, in weather prediction, in beaming all these programs for you, the satellite communication, so on and so forth. And of late, over the last 5 or 10 years, when we are driving in a car and we are making use of GPS, that is also due to the satellites. So basically what you have done is to put a whole array of satellites around the Earth. Some of them are low-lying, some of them are very far away, depending on what the needs are. These satellites talk to each other, and then they are able to help us observe what is happening in the world all over the place, monitor weather change, monitor climate change, and help us in communication, so on and so forth, as I told you. Therefore, it is a good time to spend a little bit of our time to understand what is happening. Of course, there are more sophisticated satellites that one can launch. For example, if you imagine something like Mangalyaan, Mars orbit mission, you launched a rocket which went all the way up to the Mars, and then it orbited Mars. So it becomes a satellite of Mars. In order to understand the behavior, the nature, the topography of Mars, temperature, whatever, the composition of the atmosphere, so on and so forth. So that is also of great interest. And satellite technology, of course, requires very, very advanced techniques and cooperation of a whole lot of scientists, engineers, so on and so forth. India is at the forefront of the countries that have mastered this technology. So you people will be reading in the newspaper how Indian satellite launchers are able to launch not only our own satellites, but satellites for Google, satellites for European countries, satellites for American companies, etc., etc. The most recent feat was when one of our rocket launchers actually launched more than 100 mini satellites, very, very small satellites, nano satellites. All of it happened within a matter of 5 or 6 minutes actually. You know, like your gun shoots bullets. So this rocket was able to shoot the satellites, and the important thing was that it was able to put them in the required orbits. That is the challenge in technology. So we have a big organization, and in fact, we have a whole education institution dedicated to that, Indian Institute of Space Science Technology. So those of you who really want to become astronomers, astrophysicists, aviation technologists should really study more, and what I am going to tell you in the next few minutes is a glimpse of what is happening. One very important concept that we need is that of geostationary satellite. So when we say geostationary satellite, what we are saying is that, so let us say we have this Earth, I will make it into a big blob, and we launch a satellite, and the satellite goes around in an orbit at a distance d, let us say from the center of the Earth. So given this distance, I know the period. Kepler's law, Newton's law of gravitation essentially gives me. But then the Earth itself is rotating about its axis. So what I want to do is to synchronize the period of the satellite with the period of the Earth. That means if I look up, suppose I launched it above me and I saw it above me, I will continue to see it above me. The other person somewhere continues to see it at the same point, because it is essentially co-moving with the Earth as far as the angular motion is concerned. So these are called geostationary satellites. So how do we accomplish that? The answer is very simple. So I should go back. I am going to write mv squared by r is equal to g me m by r. Okay, I use the distance d, so r equal to d. This is the distance from the center of the Earth. That is what I have. I should put an r squared here. So I cancel this. So I cancel this. And now I will write v equal to omega r. In fact, that is what we were doing earlier also. Therefore, what am I going to get? I am going to get omega squared r squared is equal to g me by r. That is what we have. So if I remember that omega is equal to 2 pi by t, that is the period. So what is going to happen now? So this will tell me that 4 pi squared by t squared is equal to g me by r cubed. Of course, all of you would be highly familiar with this expression. I may have a problem, because you see t squared by r cubed is a constant. 4 pi squared g me is what you have. So if I were to write the expression for t, what will this be? My t squared is essentially 4 pi squared r cubed over g divided by the mass of the earth. So I do the square root, and I get the period. So what do I do now? What I do is to demand that this T is equal to 24 hours, which is 24 into 3600 seconds. That is what I will do. The only parameter that I can change is r, the distance from the surface of the earth. So, well, you know gravitational constant, you know me. I cannot convert it into acceleration due to gravity because this r is the distance from the surface of the earth. Therefore, if you want, I can write r equal to re plus d. That is a better notation, and this d is what I have to adjust. So I won't spend any time working this out. So if you did that, you will get d to be a very, very large number of the order of 28,500 kilometers, which is practically giving the escape velocity, except that it will also have a horizontal component of the velocity, because of which it will be in a circular orbit. We have to understand that. That is what we are doing. This is a very large number, and that means you need a really very, very powerful rocket to launch this. So these are the geostationary orbits. Now what is the advantage of the geostationary orbits? The advantage has been very well described in your book, which I was looking up today. You know, our Earth has an atmosphere, and the uppermost part of the atmosphere is your ionosphere, basically ionized gas. So when you try to do radio communication, ionosphere reflects radio waves. So suppose I send a beam here, it gets reflected at this particular point, and it can reach, depending on the direction at which I went, it can actually get reflected, and it can reach various parts of the earth. That is how we are going to propagate that, through repeated reflections. But televisions require microwave range, radiation in the microwave range, and my ionosphere does not reflect. So the big question is, how is it that a satellite channel is able to beam its programs all over the earth? So what you now do is to put a geostationary orbit, and my satellite antenna, my emitting antenna is sitting here, whatever that thing is, broadcasting antenna. It sends microwaves which goes there. Now my satellite takes it, synthesizes it, and beams it. That is what it does. So you can imagine if you had, for example, 2 such transmission stations, and there are 2 such satellites, that may not necessarily be the way it works. So this will take care of this part of the hemisphere, this will take care of this part of the hemisphere, it can beam. Again, my ionosphere is not going to interfere with the propagation of the microwave, and you are able to see your football matches or whatever program that you want. So this is the advantage of geostationary satellite, but as I said, this requires putting satellite at a very, very large distance. Now there is another category of satellites called polar satellites. The geostationary satellites are in the equatorial plane and they go round and round. My polar satellites, so if I did that, their motion is from north-south, north-south, north. So at some point they will be above the north pole, and they come down, they will be above the south pole, so on and so forth. That is this motion, and these are all low level satellites. So what is happening in the case of these low level satellites? For the geostationary equatorial satellite, it was sitting at the same latitude, whereas here you are cutting across the latitude because you are moving north-south or south-north. Therefore, you are able to monitor the weather depending on whatever your velocity at different times of the day at different parts of the earth. It is useful for remote sensing. It is useful for a whole lot of things. For example, I want to know the rate at which the continents are drifting. I want to send signals and I want to get them back. I want to know how the clouds are moving. I want to know how the cyclones are developing. These are all very, very important. For this, these low level satellites, maybe 500,000 kilometers is what they are, They are launched barely above the atmosphere, and these are also very important, and India has launched a whole lot of them. So much so that recently when there was this highly threatening cyclone that was threatening to hit the Orissa seashore, there were a lot of foreign satellite weather monitoring centers which were saying that all the people should be evacuated because it is going to wreak havoc. But the Indian Meteorology Department was confident that such a thing would not happen. They did not evacuate people, and they were proved right because they were in possession of very, very accurate data which came from the observation. So these satellites are also very important. So I think we have fairly covered all the topics that we wanted to cover. So what I want to do is to conclude this lecture by one very simple concept, namely weightlessness. And probably, if I have time, I will also tell you something about the scientific creativity that one shows when one is launching satellites or rockets. But first let us discuss weightlessness. I had almost forgotten that. Now let us say that we have a spring mass system. Okay, so this is another block, is that okay? And this is in a table, on a table, whatever, okay. Now if I were to move the table on the surface of the earth, the whole table moves, nothing happens to the spring mass system because it is simply moving equipotential surface and this is moving at a uniform velocity. Nothing happens to the spring mass system. So this distance remains the same, and if it is in the equilibrium position, it is in the equilibrium position. However, if I have an elevator and then I put a spring and I put a mass, what is going to happen now? This mass is going to come down. That is the concept of weight because of the gravitation. Because here, while this mass is free to move, the top mass is not free to move. Therefore, there is a tension that develops. The gravitation will pull it a little bit down. The potential energy is stored here, and then the bob executes a motion, oscillatory motion. That is what is going to happen. And the most important thing is that this is not free to move. Now suppose I remove the support and I drop the whole thing. The top portion and the bottom portion, so the whole thing drops, free fall, that is what it is called. They move with the same acceleration. Now there is no tension that is building up. The equilibrium position remains the same. There is no elongation in the spring, or there is no compression in the spring, and that means my weight, this body has become weightless. This body has become weightless, and this is something that all of us experience. For example, when we suddenly trip and we are about to fall, there is a momentary weightlessness. So what is essentially happening is that in the rest frame of the body, there is a centrifugal force which acts upwards, which cancels the downward gravitational force exactly, and there is practically no force that is acting on it. So this is what is called as weightlessness. The mass remains the same, but weight changes. So let us remember, this is mass, mg is the weight, and we are saying that the body does not experience any acceleration because it is freely falling. What do I mean by acceleration? This body does not experience any acceleration with respect to the spring, whatever the top body is. That is the weightlessness that we are speaking of, and this is the same psychological feeling that we experience when, for example, as I told you, there is a momentary free fall. So people who dive from a swimming pool and from the diving boards of a swimming pool, tall diving boards of a swimming pool, experience this feeling of weightlessness very, very well. And this weightlessness is of course there even when you are in a free space, because you are not going to experience any force. Therefore, what we are essentially trying to say, you may not be able to understand at this particular time, is that a freely falling body is as good or as bad as a body in the body in a free space without gravitational field. I will not say anything more than that. This is the basis actually of Einstein's principle of equivalence and general relativity, but we will leave it at that. To conclude, I want to give an example of ingenuity in rocket launching, and that was in our Mars orbit mission, Mangalyaan. This is a very famous story. You might have heard of it in newspapers or in on TV shows, etc., etc. How is it that we are able to send a rocket to Mars? Now, once the body goes in free space, there are no external forces acting on it. Therefore, what you have to do, it continues to move with uniform velocity. But then, if you want to reach your target as early as possible, then you are in for trouble, because in free space there is no other force. So what do? You take a rocket and then you burn the fuel, so that this backward thrust actually gives you the enough acceleration. That is what you do. And this is exactly what NASA did when they sent, of course, their rocket was much heavier, when they sent their rocket on Mars mission. What Indian satellite scientists did was something slightly different. They said that there is another way of actually accelerating. So what they did was, this was my surface of the earth. You launch a rocket and my sun is sitting here. So it goes sufficiently close such that the gravitational force of the sun is not negligible, and this rocket was put in a highly elliptical orbit of the sun. Now the minute you are in a highly elliptical orbit of the sun, gravitation comes and says there is acceleration, there is acceleration. And not only that, the acceleration is natural. You don't have to put anything because it goes round and round. So what you do is to wait until you get as close to Mars as possible. So this mathematics you have to work out. As soon as you reached as close to Mars as possible, because of this acceleration, you did not have to spend any fuel on that, because the sun's gravitation was doing the job. Then you fire some secondary rockets and put it on an orbit around the moon. So this was an extraordinary feat which was out of the box thinking, as people say, which was held. Apparently it also saved a lot of money, so there are big monies that are involved. So the total money spent on Mangalyaan was about 450 crore rupees, whereas today even big Hollywood or Bollywood movies have a budget of the same order. If you look at any of the movies, one example that was given was that of Gravity. I think this was deliberately chosen because we are looking at the gravitational field. The budget of this movie called Gravity was much more than the budget of Mangalyaan. And in our own country, recent Bollywood movies have had budgets of 250 crores, 300 crores of that variety. So we see that it is one thing to know the principles, it is another thing to put it to good use. And that requires solving lots and lots of problems and constantly thinking on it. I hope you would do that. Let us conclude this set of lectures on gravitation at this particular time. Best of luck.